Controls. You might love them, you might hate them. No flow cytometry experiment is complete without them. Welcome back to our Introduction to Flow Cytometry series. In case you missed any of the previous episodes, you can find the links in the description below. In today's episode, we're going to be talking about controls, why you need them, and how to choose them, and why they're an important part of every flow cytometry experiment. In any flow cytometry experiment, there are 5 main classes of controls that you will need to consider. First up, we have the instrument controls. Every instrument will need to be quality controlled to assure performance over time. This is generally done with calibration beads, such as the CS&T or cytometer setup and tracking beads on the BD platforms, or other calibration beads on other platforms. Now, what these beads are monitoring are things like fluidics, PMT sensitivity, and laser delays, all things that are critical to producing good data on an instrument. Make sure that these calibrations are run daily, ideally, or at least before you run an experiment. If you're operating in a core facility, it's best to check with the core management team to see when these calibrations are done. Next up, we have the compensation controls. If you're only using one color, you're in luck. You can skip these. However, anytime you have 2 or more colors in your experiment, you will need to run compensation. As a quick review, compensation is essentially correcting for the spillover of fluorochrome emission into channels in which you don't want to be detecting the fluorochrome. So as you can see by the FITC emission here, most of the FITC signal is detected in the 530/30 filter. However, some is detected in the 585/42 or the PE filter. So compensation is really just there to remove this off-channel fluorescence. Now, the theory of compensation is fairly straightforward to understand, and executing it is also quite simple. It relies solely on a set of very well-defined controls. In order to compensate, all you need are a set of single-color stain samples for every color that you have in your experiment. There are some caveats though, so you always must follow these rules when setting up your compensation controls. Rule number 1, the fluorochrome in your experimental sample and your compensation control must be exactly matched. So looking at the emission spectra here, even though FITC and GFP have very similar emissions and would be detected in the same filter, they will not compensate the same way due to the slight differences in the spectra. So in this case, a sample stained with FITC would need to be compensated with FITC, and a sample stained with GFP must be compensated with GFP. They are not interchangeable. When working with tandem dyes, you must use the exact same vial of antibody on your compensation controls as you have on your experimental samples. This is due to lot-to-lot variability in the chemistry of tandem dyes. So similar to how FITC and GFP cannot be used to compensate each other, slight variations in how tandems are made are going to result in the same issues in your compensation controls. So when you're running compensation with tandem dyes, make sure you use the exact same vial of antibody across all your samples. Rule number 2, compensation controls need to be at least as bright or brighter than any of your experimental samples. This is because compensation cannot be extrapolated. So the brightest signal in your control is going to be the point at which your compensation can no longer be accurately calculated. So by making sure that your compensation samples are brighter than your experimental samples, you'll ensure that you have correct compensation through the entire range of fluorescence on your experimental samples. Rule number 3, autofluorescence must be matched between your positive and negative controls for any color. So for example, if you use unstained cells as a universal negative, so you're negative across every channel, and then for each of your positive controls you have stained beads, you're going to have a mismatch in the autofluorescence between your negative and a positive. The easiest way to work around this is for each individual compensation sample to set a negative gate and a positive gate. And that way your autofluorescence will always be matched. Rule number 4, collect enough events. The accuracy of your compensation relies on having enough negative events and enough positive events to accurately calculate the median intensity of each of those populations. If there's not enough events in either of them, the accuracy of your compensation will be affected. So when collecting your compensation samples, I recommend increasing the number of events beyond what the default setting in the software may be. A few extra tips to help you in your compensation journey. When working with a viability dye, ensure that your compensation control has some dead cells in it. Like I said previously, you need enough positive events and negative events to have accurate compensation. If your viability dye compensation sample is all alive, you'll be lacking the dead cells in order to have this accuracy. When working with activation markers or things like cytokines, I recommend, if you're using cells, to work with activated cells. In this way, you'll have a strong positive signal that should be as bright as your experimental samples. If you work with unactivated cells, you're unlikely to achieve this. The next group of controls are the gating controls. In early flow days, this was generally your unstained cells. Unstained cells will tell you about the autofluorescence of your population, but will not tell you where to set your gate. Previously, people have used isotype controls to set this gate boundary. However, isotype controls you should think of as more of a protocol control rather than a gate setting control. The proper control for setting gates is the fluorescence -1, or the FMO control. In order to set up an FMO control, essentially what you do is have your panel of interest and then systematically subtract one fluorochrome at a time. So if we have, say, a 4-color panel with FITC, PE, PE Sci 5, and PE Sci 7, our FITC FMO control will have all the dyes except for FITC. Our PE FMO will have all the dyes except PE, and so on and so forth. And by doing this, then we're going to factor in not only the autofluorescence, but also the spread of the background that occurs by adding fluorochromes to our cells. And in this way, we can set a highly accurate gate boundary in order to study our populations. FMOs will really fall into that love them or hate them category. You'll love them because they'll save your butt when it comes to setting your gates. However, you'll hate them because they are a little bit of a pain to set up. So when you're thinking about whether or not you need an FMO, consider a few things. First off, if you're working with a large parental population that has a well-defined negative and a well-defined positive, like CD3, which is a universal marker for T cells, you probably won't need them because discriminating negative and positive will be very straightforward. However, if you're working with an activation marker or a cytokine or anything that doesn't have a clean discrimination between negative and positive, you should always have an FMO. So this will be things like plots where your negative just kind of trails into your positive. So when thinking about FMOs and which ones you may need or may not need, always make sure you have them for samples where accurate discrimination between negative and positive might be challenging. Now, FMO should also be used anytime you're dealing with rare populations or low expressed antigens. And this is because those gates are generally challenging to set. So having an FMO will ensure you have the correct boundary and are looking at an accurate representation of your positive events. As a general rule of thumb, with any new panel or with any new experiment, I recommend running FMOs for every single marker you have in your panel. After that, you can use your FMOs to assess which ones may be needed in the future and which ones may not be. And that brings us to class number 4 of controls, the isotype controls. These are probably the most controversial of any control. When thinking about isotype controls, I like to think of them as a protocol control. So essentially they'll tell you if your staining protocol has potentially some issues. So I like to use them whenever I'm working with cells that I know have a lot of Fc receptors, or whenever I'm doing an intracellular stain and I might have antibody trapped, unbound inside my cells. I then use these to determine if I need to adjust my protocol with my samples in order to get a nice clear staining with my antibodies of interest. Using an isotype control will tell you things like if your blocking was complete enough, or if your washes were adequate to remove all the unbound antibody. And that is what I would recommend using isotypes for. Do not use them to set gates, ever. That is your FMO controls. Your isotypes will tell you about protocol, and if your protocol is working, not where your gate should be placed. Last up, we have our experimental controls. These are going to be your standard negative and positive controls that you should have generally for any experiment. Your negative control will give you the background level of expression of your markers before you applied whatever treatment or stimulus you've given them. So it's a nice way to just look at shifts in population and make sure you don't have a huge amount of activation in your untreated cells. A positive control will tell you if your protocol worked. So for example, if you're starting a new, say, viability project, a positive control would be something that you know will kill your cells. So if you see good viability staining, as in good death in your positive control, you know your protocol is working. So if anything weird comes up in your other samples, you know that your protocol was okay and it was something to do with your treatment. That's essentially what a positive control will give you. A control to show that your protocol has worked on your samples as you intend it to have worked. Finally, you can also consider reference controls if you're doing a longitudinal project or looking at a number of different patients over time. A reference control is something that you use every single experiment to show that your staining pattern hasn't changed over time. This could be something like pooled blood samples or a cell line or whatever you choose, just something that's treated the same way to show a standardization of your responses and your staining pattern over time. So those are the 5 main classes of controls that you will need for standard flow cytometry experiments. As you can imagine, they can add up pretty quickly. So if we go back to our 4-color example where we had FITC, PE, PE Cy 5, and PE Cy 7, let's walk through the controls that we would need. So first off, we're going to have unstained cells, again to tell us about the autofluorescence of our population. We're then going to have our 4 compensation controls, so either cells or beads stained with FITC alone, PE alone, PE Cy 5 alone, and PE Cy 7 alone. So that brings us now to 5 samples. After this, we'll have our FMO controls. So remember, in our FMO controls, we're systematically removing 1 fluorochrome at a time. So with our 4 fluorochromes, we're going to have 4 FMO controls. So our FITC FMO that has no FITC, PE, PE Cy 5, and PE Cy 7, all done the same way, subtracting that single fluorochrome. And that brings our sample total now to 9. Now for this experiment, let's say we have a mix of intracellular stains and cells with a lot of Fc receptors, so we do want to check our isotypes. Lucky for us, we can get an isotype in each color and mix them all in the same sample like we would do in our samples. So looking at our isotype controls, this only adds 1 more sample, bringing then our sample total to 10 before we've even gotten to our experimental samples. Finally then, adding in our negative control and our positive control, we now have 12 samples that we need to account for as our controls before doing our experimental samples. So you can imagine, as the complexity of your experiments and your panels increase, the number of controls you need is going to grow rapidly. So this is something very important to consider when planning your experiments to ensure that you have enough material not just for your experimental samples, but also for all the controls that you will need. And now that you know everything you need to know about controls, that brings this episode to a close. So make sure you've clicked the subscribe button and hit the little bell icon so you don't miss any future episodes. And with that, we'll see you in the next one.